Welcome to this video on amplitude modulation with carrier. This technique enables efficient broadcast communication through synchronized envelope. Amplitude modulation, or AM, is a technique where the amplitude of a high-frequency carrier wave is varied directly by the message signal. The carrier transports the signal, while the envelope carries the information payload. The strategic purpose of AM is threefold: efficient broadcasting over long distances, receiver simplicity, enabling cheap, low-power devices, and robust coverage suitable for regional and national radio. The key advantage of AM is its economic scale, achieving 90% lower receiver complexity. This is accomplished by shifting technical complexity to the transmitter, thus eliminating complex carrier synchronization circuits in consumer hardware. The limitation of double sideband suppressed carrier, or DSBSC, is the high cost and technical overhead. Coherent detection requires the receiver to generate a local carrier perfectly phase-locked to the transmitter, necessitating complex circuitry like phase-locked loop. The practical advantage of including the carrier wave alongside the message sidebands is the key to high-performance, low-cost demodulation. This design choice fueled the global transistor radio revolution, making information accessible to everyone. The design philosophy is encapsulated in the quote, "The brilliance of AM with carrier lies not in its efficiency of power, but in the radical simplicity it offers to the end user." The baseband message signal, denoted as MT, is the information payload. This low-frequency waveform represents the audio or data intended for transmission. The high-frequency carrier, CT equals AC cos omega chord, acts as the transport medium. It is a pure, high-frequency sinusoidal wave before modulation occurred. The DC offset, represented by A, is a constant bias added to the message signal. This lifts the baseband signal to ensure the combined signal remains positive, providing the carrier foundation for amplitude variations. The AM signal's mathematical model, S of t equals A plus MT cos omega chord, is the product of the biased message and the carrier sinusoid. Expanding this equation reveals the transmitted carrier term and the information sidebands. The AM frequency spectrum consists of three main components: the carrier, a discrete impulse that facilitates detection; the upper sideband, the shifted message spectrum above the carrier; and the lower sideband, the mirrored message spectrum below the carrier. The central carrier impulse, found at plus or minus omega c, is a powerful impulse that manifests from the DC offset A. While it consumes power, it serves as a crucial frequency and phase reference for simple detectors. The modulation process creates information sidebands by effectively copying and shifting the baseband message spectrum. The total bandwidth occupancy of the AM signal is twice the maximum frequency of the baseband signal. The critical envelope condition requires that A plus MT is greater than or equal to 0. For successful recovery via simple envelope detection, the combined signal must never cross the 0 axis. If the message is too strong, the envelope will distort. This envelope condition is critical for four main reasons: zero crossing protection, envelope fidelity, distortion avoidance for non-coherent receivers, and circuit reliability, which allows the use of inexpensive diode-based detectors. When the message signal is too strong, overmodulation occurs, causing phase reversal. The receiver's envelope detector follows the absolute value of the signal, leading to extreme clipping, harmonic distortion, and loss of the original information. According to modulation theory, when phase reversal occurs, the simple envelope detector is deceived, following the absolute value of the signal and creating catastrophic distortion. The simple envelope detector, or non-coherent demodulator, consists of only a diode, a capacitor, and a resistor. It recovers the signal by charging the capacitor during carrier peaks and slowly discharging during troughs. Demodulation has three steps: rectification, where the diode passes only positive half cycles; filtering, where the RC circuit smooths the pulses into an envelope; and recovery, tracing the biased message signal. The RC filter's time constant must be slow enough to ignore the carrier frequency, but fast enough to accurately track the message changes. This ensures a perfect balance between charging during peaks and slow discharge between peaks. Final signal extraction involves DC removal, where a blocking capacitor subtracts the DC offset A from the recovered envelope. The final result is the successful reconstruction of the original baseband message signal, MT. The modulation index, denoted by mu, is a dimensionless parameter indicating how much the carrier amplitude is varied. It is the key metric for ensuring distortion-free transmission and high power efficiency. In the symmetric case, the modulation index mu is calculated as the ratio of the message signal's peak value, MP, to the DC offset A, where A is the unmodulated carrier level. The operating ranges of modulation are divided into 3 cases. Under modulation, mu less than 1, which is safe but inefficient. Critical modulation, mu equals 1, which is distortion-free and highly efficient. And overmodulation, mu greater than 1, which causes catastrophic signal distortion. Overmodulation, where mu greater than 1, causes the signal envelope to vanish at 0 crossings. This creates sideband splatter, which interferes with adjacent channels and destroys audio clarity for the receiver. For the non-symmetric case, the modulation index can be calculated directly from an oscilloscope view of the modulated wave envelope, using the maximum and minimum amplitude measurements, AMAX and AMI.